Hello class, it's Mr. Hofstede. Let's take a look at Unit 5, Unit 6, Lesson 5, Fission and Fusion. I'll just go over the notes here. There's a separate video for the examples, but I think it's worth just going over the definitions a bit and what's happening with these reactions. So, first off, we got artificial transmutation, which isn't quite fission or fusion, right? It can only be done in a lab. It's closer to fusion, I would say, as we're kind of adding together two nuclei to create one larger one. So fusion is always fusing stuff together. Fission is creating fissures, I like to think of it, or splitting things into two. So with artificial transmutation, originally Rutherford bombarded nitrogen-14, which was stable, with an alpha particle, and it caused it to transmute. And transmuting is becoming a different element. So this stable nitrogen is becoming oxygen, and we're also getting a little hydrogen atom out of this as well. So you often see that, whether it's hydrogen atom, you could even get neutrons, right? It'll usually be some additional particle or atom along with our larger transmuted particle. So this was done in 1919, and after that scientists wanted to create new elements because that's pretty cool, right? Tony Stark did it. Why wouldn't we all want to do it? They did it using particle accelerators, so essentially bringing these particles like alpha particles to super high speeds, right? And we'll get more into that later. Anything beyond uranium on our periodic table of elements is artificial, and none of them are stable. They'll all decay over time. They'll have different half-lives, they'll last different amounts of time, but none of them will remain stable. So this example you can find in the attached video. The math for this lesson isn't too tricky. It's kind of a nice break. We are more just working with simple algebra and conservation of nucleons, as well as conservation of charge, our principles of physics 7 and 8. So give those a shot. They're not overly difficult. We just need to get out our periodic tables of elements and do some addition and subtraction. Good break. All right, fission. So this is when we're breaking things apart. Like think about fissures, which are little cracks. You're cracking apart larger nucleus into two smaller nuclei. Weirdly enough, it's triggered by a slow-moving or low-energy neutron. I almost like to think of it like a little drill neutron. It's just going along slow, but it has what it takes to split or drill apart this parent large nucleus into the two daughter nuclei, two smaller. So with fission, we'll always start with something much larger with a higher mass number, higher atomic number, and it'll require a neutron, low energy, slow moving. That's important to know, and that'll split it into two. We'll also always get 3 other neutrons, right? And each of those 3 can trigger new reactions. So you can get this super quick chain reaction, right? Exponential growth. And yeah, this is why it's such a powerful source of energy or such a dangerous bomb, depending on whether it's controlled in nuclear reactors with the proper safety measures taken to not allow this to get out of hand like it did in Chernobyl, or if it's uncontrolled, it becomes super deadly, dangerous bombs that just keep on reacting, keep on growing and increasing. So we have a mass defect from our atomic mass. Our nucleons are conserved, but we're having a mass defect because we're having different amounts of this strong nuclear force the quirks and the quarks holding themselves together, and that mass defect will be converted into the kinetic energy of the neutrons and nuclei as they break apart and spread out into the world. And we're also going to get gamma rays, gamma photons, which is in this case dangerous, and this is why nuclear reactors need to be so carefully monitored. And that's one of the big disadvantages. We get this radioactive waste that's very expensive and hard on the environment, because you essentially have to bury it in sealed supermassive containers with meters of concrete and lead surrounding them. So that's the biggest disadvantage to our fusion reactions and our nuclear energy, which we're hearing a lot about in the news, especially in Alberta, thinking about making the shift away from coal, which is really good. Almost 2 million times more energy per gram or per kilogram, or however you want to look at it. So it's a far more efficient form of energy. It just has its disadvantages as well with this nuclear waste. And it's still non-renewable, right? There is a certain fixed amount of uranium on our planet. A lot of it happens to be in Saskatoon. We have one of, I think it's the second largest uranium deposit in the world, just next door. But it will eventually run out. So it does offer a short-term advantage, right? A short-term benefit in terms of energy, with lots of advantages over coal and gas, but it can't be our forever fix. All right, so whenever you're doing the homework questions, thinking about a slow-moving neutron, right, splitting, and we'll always get 3 neutrons. So those are kind of some of the key things that are telling us that we're working with a fission reaction. All right, you can find that example on the other video as well. All right, our last kind, fusion, right? We're fusing together the nuclei. So it's the exact opposite. Well, not exact, but it's very similar to fission in the reverse order. So we start with small nuclei, we're going to fuse them together, and we end up with our larger nuclei. So this so far can't be done in a laboratory. Maybe it can now. I don't know. I haven't researched it in a little bit because it does require such high temperatures. So it happens quite naturally all the time in the sun. This is the form of energy that really provides life on Earth, and it's the source of the vast majority of energy in the universe, because this is happening in all stars where we have extreme high temperatures. We have these ionized molecules, ionized atoms, and they're colliding at super high speeds, and they are forming these larger and stable nucleus, right? And you can even get fusion of these slightly larger molecules, and you can create carbon, right? Any atom essentially ever was created through some sort of fusion reaction. It just depends on the heat and the size of the star. All right. So fusion of deuterium and tritium. So that's deuterium, that's tritium, right? 2 nucleons of hydrogen, 3 nucleons in hydrogen. So 1 proton, 1 neutron, 1 proton, 2 neutrons. Those are going to collide at extremely high speeds, fast enough that their nuclei are able to essentially, fuse together. They come into such close contact that the strong nuclear force is kind of overcome, and then combines all of our nuclei together, minus this one neutron. This one, neutrino. Neutron. Not a neutrino, sorry. So we get, again, this mass defect as these four nucleons are within the nucleus. There's a bigger mass defect than the starting nuclei, the small nuclei, and that mass defect produces a ton of energy, right? Lots of it is going into the kinetic energy of our neutrons and our stable daughter nucleus, and we're also producing gamma photons as well, right? So this has an extremely high yield of energy. Advantages: it's abundant fuel, we got stable byproducts, right? All we need to use is these abundant deuterium and tritium atoms. Disadvantage: we need to be super hot, like as hot as the center of the sun. So not super feasible. The greatest scientific breakthrough ever will probably be cold fusion, and if we do find a way to emulate this reaction at a lower temperature, then we will probably have more energy than we could ever possibly use, just right at our fingertips. All right, good luck with the homework. Again, it's pretty much all conceptual with a tiny bit of simple algebra. Make sure you're paying attention to which types of reactions they're asking and you're working with. And yeah, let me know if you have any questions. Good luck. Talk to you later.